So on this presentation, we're going to start to talk about how does the building code actually put into numeric values some of the expectations for a future tsunami wave. We're going to talk about how we can quantify the amount of internal moment that will form on a slab in a building due to a potential tsunami. So I'm going to share my screen. And we're going to look at how we determine these loads that a slab may need to support during an earthquake. So this is example 1.9. I know the location of my project, the latitude and the longitude, and my structure is going to be very simple. We're looking at a rectangular slab, 25 feet by 75 feet. Slab is 10-inch thick, normal weight concrete. There's this 4-foot tall pony wall all around the perimeter of the slab, and we're being asked to determine the ultimate level loads according to ASE 7-16. We're told that the top of the slab is going to be 3 feet above the NAVD 88 line, and the top of the perimeter wall is 7 feet. And as an engineer, we're going to consider two different structural models for this slab. One would be that the slab is simply supported, and the second would be the slab is rigidly attached to the pony walls, and the slab actually helps support or resist the forces that are being applied to the pony walls. Because this slab is so long and narrow, it's going to be considered a one-way slab. So the first thing I'm going to look at is the gravity loads. Now, we haven't really been told whether this slab sits on the ground or is supported, but I'm assuming that if it's going to be a simply supported slab, it's going to have a support at the two ends of the slab. This slab has to support dead load. The dead load is the weight of the concrete itself. That'd be 10-inch concrete, 150 pounds per cubic foot, or 125 pounds per square foot. But we're thinking of this as a beam that is 1 foot wide. So on that 1 foot width, the dead load will be 125 pounds per lineal foot. And the live load was given to us as 100 pounds per lineal foot. I'm trying to determine the ultimate moment in the middle of this slab. So for a simply supported beam, it's going to be 1/8 the uniform load, the span squared. So in the middle of this slab, there's 9.77 kip feet of moment per foot of width of slab, causing tension on the bottom, and the live load is a little bit smaller than that. Now I have to begin to think about a potential tsunami wave. I'm told the latitude and the longitude of my location, and if I go to the ASC tsunami hazard tool, I can find that marker, the lat and the longitude, and I'm told that the run-up elevation is going to be 8.76 feet above NAVD 88. Since that run-up elevation is higher than the top of the wall, then when the wave is fully in, the complete item will be submerged. Really, the most critical thing for me is when the water is right at the height of 7 feet and has filled the surrounding area, but it has not flooded the slab itself. So the loading due to the tsunami water is that the water is actually trying to lift this slab and wall upward, picking the slab up with hydrostatic pressure. So if I look at my hydraulic or my H due to the tsunami, First off, it asks me to calculate the tsunami water density, gamma S sub S. So the code tells me that I should expect the specific or the density of water to be 64 pounds per cubic foot, which is a little higher than what we normally consider. But the reason we do this is because it's actually seawater from the ocean and not fresh water. But then the code also tells me I need to increase that by multiplying by this K value of 1.1. That 1.1 is the fact that this wave is also carrying a lot of debris, soil, broken buildings, cars, whatever. So the density of the water during the tsunami is actually higher than it will be when that debris settles out. So the code tells me I should expect a density of water of 70.4 pounds per cubic foot. So when this wave gets to the very top of that wall, the pressure at the top will be 0. The pressure at the top of the slab would be 4 feet by 70.4. The pressure at the bottom of the slab would be 4.83 times the density of water, or 340 pounds per square foot. When the water is inflowing, it's fully surrounding the slab and the walls. There's no water assumed inside. So my hydraulic pressure is 340 pounds per square foot. Now, my second condition is once after this entire area has flooded and now the ocean water begins to recede, the water is outflowing, but for some brief time, this entire shape may be like a bathtub and may be completely filled with water. Now, maybe this slab is a slab on grade, and if so, then all the weight of this water is simply being pushed right down onto the soil below it. But we're considering this as a structural slab with supports at the two ends. And perhaps one reason to do this, even if it's on the ground, is the fact that we expect the soil may be settling away or may not have very much strength to begin with. So is it realistic to build a structure that holds this water? I mean, isn't there got to be a door somewhere around this perimeter? Well, yeah, there probably is a door. And through that door, this water would be draining out. But you're thinking about a rather narrow door with all of this water inside. It does take time for that to drain out. And as engineers, we're going to take the conservative approach that at least for some short period of time, this slab has to support all of the water inside this tub. So in this case, I have the pressure at the top of the wall is still 0. Now the pressure at the top of the slab will be that 282 pounds per square foot that we talked about before. So I was told to consider two different structural models. The first one being the idea that this slab is simply supported one-way slab. That tells me that in this inflowing case, there's 340 pounds per square foot on below pushing upward. I'm going to get a moment of 26.5 kip feet per foot of width of slab, causing tension on the top of the slab. The second time, I actually have the pressure pushing down on the slab. Now I get a moment of 22 and a little over 22 kip feet, but this one's creating tension on the bottom of the slab. So if I pull all these calculations together, I know the dead load moment, the live load moment. Now I have two different conditions for the tsunami wave. I only need to consider one at a time because they obviously don't both occur at the same time. And I'm going to use a negative sign for this case where the tension is actually occurring on the top of the slab. So ASC 716, section 6833 tells me that for tsunami action, there are two load combinations I need to consider. One is 0.9 times the dead load plus the tsunami force. The other is 1.2 times the dead load plus half the live load plus that tsunami force. So I put these together. I need to remember that some of these moments are opposite the sense of the others. And I get two options for the first load combination, two options for the second load combination. The critical cases will be this first negative 17 and this positive 37.6. Now, with experience, most engineers begin to realize that, well, these crossed out load cases are never the worst condition. If I'm doing this by hand, I'm not going to spend my time calculating them. But of course, on the other hand, anymore, it's very common that engineers are setting up a software program and just putting in every load combination possible and then telling the software to select the most extreme events. The other thing I need to keep in mind is these are only the load combinations considering the tsunami wave. The slab, of course, has to also be designed to resist any other load combination, such as 1.2 dead plus 1.6 live. Now, when I think about option two, now I'm going to start to think about the fact that I do have a pressure on the side of this that's actually creating a moment on the end of this slab. So I'm not going to have a true simply supported beam. I actually have more of a cantilevered system. To solve this, I'm going to cut a free body diagram where I cut it exactly in the middle. I can replace that triangular distributed load with a single force. And the system technically is indeterminate, but I'm going to assume that the end reactions are those that are required to support the vertical applied loads. And of course, due to symmetry, there's going to be some expectation that the shear has to be zero in the middle anyway. So looking at this inflowing water, I can determine how much my reaction will be. Then I'm going to use equilibrium to solve for these other three. That compression force is going to have to equal whatever my horizontal pressure creates. The shear in the middle will turn out to be zero. And to get the moment, I'm going to have to sum all the moments due to this reaction, the pressure below the slab, the pressure on the side of the wall, summed about the center of the slab, gives me a moment of 25.5 kip feet tension on the top of the slab. On the outflowing water, my condition 2, now I have water on the inside. This internal pressure creates a horizontal force. My reaction is going to be a little smaller due to the weight of the water. Now I'm going to work my equilibrium. Now my internal force is actually a tension force on this slab. The shear still turns out to be zero. And the moment in the middle due to the tsunami wave is now creating 22 kip feet, a tension on the bottom of the beam. Once again, I'm going to put those 4 different types of loads together. I've still got the same dead and live load. I've got my 2 different conditions for tsunami loading. I cross out the cases that won't be the worst, and instead I look at the possibility of the largest negative moment and the largest positive moment, and I put those down as my critical effects. Of course, I also need to think about the axial force that's being developed in this slab. Those also would be load combinations of axial force. But the reality is those forces are so small that I'm going to neglect it. And the effect of the force on the wall is really very small compared to what I had when I considered option one. So now I'm going to compare the two results of my two different options. I had a positive and a negative moment, tension on the top or the bottom. The worst of those two is going to be this 17.7 for tension on the top of the slab, or 37.7 kip feet for tension on the bottom. The reality is the choice of which structural model I used really didn't affect very much the numeric outcome. Now, these load combinations have to be compared to everything else in a traditional load combinations. I haven't taken the time to do that, but that would just be traditional concrete design. The primary effect due to the tsunami load is going to be the realization that I actually have to hold this slab down on the ends. And I do have a rather large negative moment, tension on the top of this beam at mid-span. Those are probably the biggest impacts due to the tsunami wave, because I probably don't have those forces being applied in that kind of a pattern due to traditional gravity load. Thank you.